I'm going to slow myself down by doing most of this on the whiteboard because otherwise I just go too fast. And I'm also going to switch the order in which I go through the material slightly from how I have it in the notes. In the notes, I go through all of the theory of norms first, and then I say, and here's a nice application of all of this stuff that's important to the class. I'm going to start by discussing that application and why it's important to the class. We will find that we can't go through all of that because the concept of how large a vector or a matrix is, we haven't defined yet. That will then give us the reason to start digging into how do we quantify how large a vector is, or a matrix. For a vector, you can sort of say, well, it's the vector length. But for matrices, it turns out that you need to actually define this. And then it turns out that when you look at how to define how big a matrix is, there are measures that are theoretically very important and convenient that in practice are really difficult and expensive to compute. And that then leads us to introduce different vector norms, different ways of measuring how big a vector is, because then the associated measure for the matrices becomes much more convenient. And that's sort of what we're going to be talking about. I wouldn't be surprised if we finish early today, but who knows. So, let's start. How many of you are completely comfortable with complex numbers? Okay, notice my hand is down. We develop software, and I will always go and say, oh, I've got this great idea for a new algorithm. I'll implement it in real arithmetic, and I'll go, well, let's write the paper and have it done with. And fortunately, there's one person in our group who's in part responsible for actually putting out software that people can use, and he always says, no, we must start with the complex case, because going from complex to real is easy. Going from real to complex is much more difficult. And at some point we need to talk about complex numbers, because when we talk about eigenvalues and eigenvectors, inherently things shift into the complex plane as far as the eigenvalues are concerned. So we're going to have to bite this bullet. So let's just remember a few things. A complex number alpha can be written as its real part, which we'll put a subscript r on, plus the imaginary part, which we'll put a subscript c on. Maybe I should have made that I. We'll make it c. Should have made it I. Whatever. Okay? Now, we know how to compute the absolute value of alpha. And notice that that's equal to the square root of the real part squared plus the imaginary part squared. And you could also compute that as alpha r plus I alpha c times alpha r minus I alpha c. Actually, I prefer doing it this way. You could do it either way. And notice that that's the complex conjugate of alpha times alpha. Okay? Where the complex conjugate of alpha is defined as alpha r minus I alpha c. Excuse me?
Shouldn't that be square root thing?
Oh, yeah, absolutely. Thank you very much. I think in my notes I did it right. Yes, in my notes I did it right. Good. And the important thing is that if alpha is not equal to 0, then we know that the absolute value of alpha is greater than 0, which is known as the positive definite condition. We know that if we multiply two complex numbers and take the absolute value, you can take the absolute value of the complex numbers first. That's known as homogeneity. And then finally, there's the triangle inequality. Okay. And, over time, you've noticed that these kinds of properties are useful. And then when you looked at 2- and 3-dimensional vectors, you sort of saw natural extensions of this. Okay, now, I actually didn't start where I said I was going to start. I was going to start by motivating where we're headed. So let's take a minute to do that. Okay. At some point in the semester, halfway through, we're going to start discussing how to solve linear systems. Okay? So we're going to look at things like AX is equal to B. Now, the fact is that an equation like that typically comes from measured data, which means that there would be some error in the data. Okay? The input typically are A and B. And let's just say that only B is measured and will therefore have some kind of error in it. Or if there's no error in B when you measure it, there might be error in B when you plug it into the computer and you represent B as floating point numbers. So inherently what happens is that you really end up trying to solve B plus some change to B. And notice that therefore the result is not exactly X, it's some perturbed version of X. Now, I'm usually big when it comes to notation. It's very easy to look at this and say, oh, that's delta times B, so some constant perturbation. But what that would mean is that if B is beta 0, beta 1 through beta n minus 1, then delta times B would be delta times beta 0, delta times beta 1, etc., where delta would be some small quantity. And what really would happen is we would claim that every entry in B was perturbed in exactly the same, was proportionally perturbed the same way as every other entry in B. Okay? That's not what happens. In fact, what happens is that you have a small change to beta 0, which would be different from a small change to beta 1. So what, in my notation, notice that I have the delta touch the B to sort of indicate that this is just a symbol for a vector where the individual entries are perturbed possibly differently, as opposed to some uniform perturbation of those entries. Okay? Got the notation straight? Okay, so now the question, of course, is if we change B, how does X change? And we would like to put some kind of bounds on that. Okay? It would be nice if we could say, well, if there's a small error in B, the answer doesn't change at all, because then we can be really sloppy in our measurements. But life is not usually that simple, right? So, what kind of thing would we want? Well, we would want to say if B is perturbed relative, well, if delta B is a perturbation of B, then it's the relative perturbation that we might be interested in. And we would like to know what then happens to this right here, right? Can we do that? Hopefully, when you took a linear algebra course, if you ever did a vector divided by a vector, you got a big red slash through your paper. No credit. Unless the vector happened to be of length 1, right? So, and notice that also, we aren't really interested in this exact number, we're really interested in its magnitude. So we're interested sort of in its absolute value. We just discussed absolute value of a complex number, right? Which then hopefully would be just the absolute value of that. But how's the absolute value of a vector defined? We haven't really defined that yet, right? So what we're going to work with are things called norms, and typically one uses double lines to indicate a norm. And one convenient norm that you have run into in the past is simply the vector length. If the length of this vector is small relative to that vector, then you know you have only slightly changed your vector. Because what happens then? A vector you can visualize as some vector. Now it doesn't need to start at the origin because a vector doesn't have locality, but it's convenient to place it there. If you then do a small perturbation of that vector, that would be something like that. And then you can see that if this is in length small relative to that, then the new vector is roughly the same as the original vector, b plus delta b. I should make that touch. I just created this notation. I should use it. You got the idea of where we're headed? And what would you like to say is, oh, the x that under A maps to this, you would hope is then a vector that's very close to the actual vector solution that you want. And then everything is hunky-dory. Okay? Now, what we're going to find is that it's possible that you change B ever so slightly, but that in changing B ever so slightly, you end up perturbing your result hugely. Okay? This has to do with matrices being almost singular. Now that's something you don't run into in your mathematical linear algebra class because you don't deal with error there. But clearly that would be a problem. Now, if you had a software company and you were selling a piece of software that solves AX equals B, and your customer comes along and does measurements in the field and throws this into your solver, and all of a sudden they get completely the wrong answer, you're going to have an unhappy customer, right? Which is why software companies need to hire lawyers. Now, if you had a really, really good lawyer, what would your lawyer argue? Your lawyer would argue, the problem is not with our software, the problem is with your problem. Right? And if your lawyer happened to be like my lawyer and a decent mathematician, and actually I have a lawyer who's a decent mathematician. Yeah, he was a master, well, he got his master's in our program, and when he applied to the master's program, he had a letter of reference from Dijkstra. I mean, the guy must have been pretty good, right? Good lawyer to have. And what that lawyer of mine, hopefully, if he paid attention in my class, I don't think he ever took this class from me, but if he had paid attention in my class, he would say, wait a minute, if it's the case that a very small change in the right-hand side mathematically can lead to a very large error, then the problem is not at all with our software, because that's a attribute that completely is dependent on the problem, and the problem is the customer's problem, and therefore you cannot blame our software. All right? Of course, the customer may come back and say, well, then prove to me that your software is something called numerically stable, which is another thing that we're going to be talking about in this class. And obviously that's also going to be dependent upon being able to reason about changes in the solution relative to the changes in the right-hand side, which is again going to involve norms. All right? So that motivates what we're going to talk about. And let's just go ahead and go back to mathematics. Let's erase all of this. We'll revisit this. We'll answer this question at the end of the lecture. But what we're going to talk about first are vector norms. So let me go ahead and scroll this up a little bit. But I'm actually going to write through it. So, absolute value is actually an example of a vector norm, except it only works for vectors of length 1, which aren't very interesting. So what's the definition of a norm? Okay. We start with a function, let's call it mu, within the Greek letter mu, and it's a function from vectors of length n 2r, then this is called the vector norm. If three conditions hold. Okay. The vector x, so here we're talking about, I need to, okay. For all x and y vectors of length n and alpha in complex valued scale, x is not equal to 0 implies that the norm of that vector is greater than 0. Let's see the equivalent of this right here. If you take the vector x and then you ask how big is it, you get exactly the same answer as if you ask how big x is and then you multiply it by the absolute value of alpha. That's the equivalent of this, that's homogeneity. And then there's the triangle inequality. If you do x plus y, you get that that's less than the lengths, the norms of these vectors separately. Okay. And if all three of these are satisfied, then you're okay. Okay, so we have something that sort of resembles absolute value, except that now we have to find it for norms. Yes?
Is the first condition to where is the if or only?
Sorry?
Is the first condition if or only if?
You could go both ways. Okay? As an exercise, this second condition tells you that n of the 0 vector must be 0. So this actually applies the other direction. Okay? So we leave it as an exercise. Everybody with me? Okay, give me an example of a norm.
Distance.
Distance, vector length, right? Euclidean distance. Okay. So let's have a look at that. It turns out that it's the norm for which it's hardest to prove that it's a norm. Because there's a little idea that you... Now, notice that in high school you were already taught that if you have a vector x and a vector y, and you add x and y together, what do you get? This is x plus y, right? That it's always the case that the length of this is less than the length of that plus the length of that. Right? Did your high school teacher prove this to you? Some of them probably did, right? If you went to a good high school, then they would have proven this. But I doubt that most people saw this. You know, it's just sort of a fact that's thrown at you. Actually, in geometry, maybe you do prove that. Oh wait, they don't do proofs in geometry class anymore in high school in this country, so probably not. All right, so how do we define the 2 norm? Okay, we're going to write this as the 2 norm, which we're going to write like that. Okay, so what was used to be the length is now the 2 norm, and that's because we're going to see other norms. And this is a function from Cn to R. And it's defined as, there's multiple ways of defining it. You can write it as the square root of the dot product of x with itself. Or you can write it as the square root of the conjugate of each element with itself all added together. Which of course is just the definition. This is the definition of the dot product, right? which you can then write as something that will look a little bit more familiar. Chi0 in absolute value squared plus chi1 in absolute value squared, etc. These are all equivalent definitions, right? And obviously, if x is real valued, then you can drop the absolute values, and you get the usual length of a real valued vector that you may have been familiar with, right? So we call this the 2 norm, so therefore it must be a norm. There's your proof, right? QED. It's not quite that simple, right? So strictly speaking, we should prove this, and let's get some exercise. And let's get started and let's see where the snag is. I actually did a proof of this that I thought would look very convincing until I started scratching my head, and then I convinced myself it was totally wrong. So it's easy to make mistakes with these things. The first couple of parts are easy. Notice that there are these 3 things that you need to prove. One thing is that if x is not the 0 vector, then the 2 norm of x is greater than 0. Well, if you look at this definition, notice that if x is not the 0 vector, then at least one of these must be non-zero. And since you're adding positive numbers together, if you add other things to it, you get something at least of that value, and therefore clearly it must be greater than 0. So I have a formal proof of that in the notes, but let's just leave it at talking through it. What's the second one? If you do alpha times x in 2 norm, you get alpha times the length of x. Well, geometrically, that's sort of how multiplying a vector by a scalar was defined, right? You stretch it, you stretch it. Or what exactly stretching means in the complex plane, it means stretching it, possibly pointing it differently than anyway. Let's not go there. Yes, this is why we should just avoid complex numbers. This is not that hard either, because notice that if you multiply x by alpha, then each of its components is multiplied by alpha, and then you can pull the alpha squared in absolute value out, and then you can pull that outside of the square root, and before you know it, you've proven this right here. Right? Again, details are in the notes. You probably don't need to go through this. This is the hard one. You want to prove that x plus y in 2 norm is less than or equal to 2 norm of x plus the 2 norm of y. That's the triangle involved. Okay? And I'm going to go through the proof, and then I'm going to show you where the snag is, the little detail that you need to get right. And then I'll state the theorem that you need to get over that little snag. And then I think I'm just going to let you read the proof of the theorem that gets you over the snag, because it's kind of technical and not really that important to the class, other than that you know what it is. So that's the strategy. And actually, often it's easier to look at the square of both sides when you're dealing with a norm, especially the 2 norm, rather than resolve itself. So what we're going to do is we're going to reason about x plus y in 2 norm squared, which by definition is just the dot product of this vector with itself. And taking the Hermitian transpose of the sum of 2 vectors just means that you take the Hermitian transpose of each of the vectors separately. So I'll put that detail think that was in the notes for the last lecture. And then if you just multiply everything out, you get x Hermitian x, let's see, yeah, plus, let's see, y Hermitian x plus x Hermitian y plus y Hermitian y. So far, so good. And this is where things get a little tricky. This here is just the norm of x squared. This here is the norm of y squared. Where we would like to end up is dot, dot, dot. But this is equal to that squared, right? Why? Because if we then take the square root of both sides, we get this, as long as there's a less than or equal to that comes up somewhere along the way, right? And there's something sitting here still. And that's where things get a little nasty. It's certainly the case that this is less than or equal to this plus y Hermitian x in absolute value plus x Hermitian y in absolute value, because if you take the absolute value, then at worst to make it bigger, right? And of course, the absolute value of this is equal to the absolute value of that. So that then would give us a norm of x plus 2 times x Hermitian y plus the 2 norm of y squared. Okay? If you multiply this out, what you get is this squared plus 2 times the norm of x times the norm of y plus y squared. Okay? So as long as we can show that this is less than or equal to that, we're home free, right? And obviously, if you wrote all of this down, I would look at that and say, person seems to know what they're doing, you'll probably get full credit and get away with it. All depends on whether our TA pays attention to the details of what you're writing down. But strictly speaking, you need to, you're depending here on the fact that this here is true. Okay? This is not immediately obvious, is it? And it's actually kind of tricky to prove. It's tricky to prove when you have real valued x and y, vectors x and y. It's trickier to prove if they are complex values. As a matter of fact, I struggled with it for about 15 minutes yesterday. So this here is known as the Cauchy-Schwarz inequality, which the mathematicians in the audience may have heard of. And its proof kind of depends on a little trick, and then it depends on another little trick that you have to recognize about complex valued things. And, the temptation, of course, is to say, I spent 15 minutes trying to figure this out. I may even have spent half an hour on it, therefore I'm going to make you suffer through it. But the fact is that the proof is in the notes, and the proof can probably be found in a lot of linear algebra texts. And it's not all that pertinent to this course, and therefore I'm just going to let you figure it out on your own. Okay? But you kind of see that it's a matter of pushing through. Now, yes, question. Oh, what's going on? Good point. Thank you. That would have been disastrous once again, right? Let's see if we can just... I actually was organized. Usually I don't carry a power cord along, but I was aware of the fact that I was getting close, so we're good. So the proof of this is actually given up there, okay? And it's not that intimidating, but there's a little trick that you have to pull that takes a little bit. Okay, any questions about that? So a fact that was sort of stated as fact in your math and physics courses when you had to deal with vectors, we have now rigorously proven. Okay? So, you may ask yourself the question, well, we've got a norm, surely that's good enough that we can just keep going. What we're going to see later in this lecture is the fact that with vector norms you can define matrix norms. Okay? And now all of a sudden you have to start thinking about what does it mean for, what meaning does the size of a matrix really have? Okay, and we'll talk about that shortly. But it turns out that there is such a thing as a 2 norm of a matrix that's associated with a vector 2 norm, which is theoretically wonderful, but in practice it requires you to compute the largest singular value of a matrix. And the fundamental problem with that is that that's closely related to finding eigenvalues of the matrix. And the problem with that is that finding eigenvalues of the matrix is closely related to finding the roots of a polynomial. And the problem with that is that Galois theory tells you that you can't find that in a finite number of steps if the polynomial is greater than 4 or 5. Okay? I always forget whether it's 4 or 5. So, theoretically you can say, oh, everything is simple. In practice, in this class, we'd like to be able to compute things. Okay? And of course, there are 2 ways of doing that. You can either come up with really clever ways of computing things. So we could spend the rest of the class trying to come up with really clever ways of computing the 2 norm of matrices. Or we can sidestep the whole problem and say, we'll just pick a different measure of how big a vector is and how big a matrix is, which hopefully are easier to compute, and then we don't have this problem. Okay? And as I always say, a good mathematician is a lazy mathematician. So take the easy way out is often a good thing. So let me teach you the easy way out. The easy way out is to use something known as the vector 1 norm. What's the vector 1 norm? Let's leave the definition of the vector 2 norm up, and let's put the vector 1 norm right here. Okay, so this is often indicated by the function with a 1 at the bottom. And if x is a vector of length n, then the 1 norm of x is defined as simply the sum of the absolute values of the entries. Already easier to compute, right? No square roots, no squares, no multiplication, absolute value, add them together, you're done. This is sometimes called the taxi cab norm, because if you imagine being in Manhattan where the blocks are laid out very nicely like that, of course they're not these square blocks, but let's pretend they are, then if you have a vector like that, then the vector 1 norm really says the distance that you have to travel is the distance that you travel along the grid. And that's how we're going to measure. Fair enough? And it's actually much easier to prove that this is a norm than it is to prove that the 2 norm is a norm. So we're going to leave that as an exercise. So by Tuesday, get some practice and prove that this is a norm. Any questions about that? So then, there is another norm that is going to be handy, and that's known as the infinity norm. And the infinity norm is defined as the maximum over all entries in the vector of the absolute value of those entries. Okay, so if we have this vector here, you look at this distance, you look at that distance, you pick the largest of the two, that's the size of the vector. It's probably a little bit less intuitive that that also is a norm, but it's actually very easy to prove that it's a norm. So we'll leave that as an exercise. All right? Now, how are all of these related? Well, there's also something called the p-norm. Which is actually given right there. And the p-norm is given by the pth root of the sum of the entries raised to the pth power. And all of a sudden it's pretty clear that the 2 norm is a special case of this, the 1 norm is a special case of this, and the infinity norm turns out to be the limit as p tends to infinity of p norm, which is not that hard to see because if you let p go to infinity, then the term that has the entry that's largest in it starts dominating, and therefore that's the one that comes out. All right? So, we've got some norms to play with now. Okay? Clearly, both of these are cheaper to compute than the 2 norm, but that's not really the issue. Computing lengths of vectors is not where it's at. It is computing lengths of matrices, or sizes of matrices. That's going to be a big problem. Any questions about this so far? Let's build your intuition a little bit. Let's look at the unit square. So let's look at all vectors rooted at the origin such that the 2 norm of x is equal to 1. How would you visualize the set of all vectors with the 2 norm equal to 1 if those vectors have their tail at the origin? It should be a circle, right? It's the vectors that have length 1, so it's a nice unit circle. Okay? What if instead we ask the question, the infinity norm is equal to 1? What does that look like?
A diamond.
Is it a diamond or a square? Actually, it's a square either way, right? It's the diamond, and it's a diamond either way. So, yes. But, you know, thinking in the obvious way, is it a square or is it a diamond? It's a square, right? It's any vector that you point to on the square will have a largest entry equal to 1. Okay? If you ask the question, the 1 norm equal to 1, then you get the value, right? Because the sum of the x coordinate plus the sum of the y coordinate in absolute value is then equal to 1. It'd be harder to picture this in a complex plane, right? Well, that's not good. What about the p norm equal to 1?
Somewhere in between.
Yeah, I mean, if you superimpose the infinity norm, then the p norm will be sort of something in between, right? Every time I teach this, I have to think, can p be less than 1? I think it can be. No, wait, I don't know. I always have to think. I think p can be less than 1. But I guess that would start looking like this, right? Probably not particularly useful, so probably not worry about it. I go on camera admitting I don't know things. What kind of professor am I? Well, I mean, it's the techniques that allow you to discover what really is going on, and therefore, what we actually know is not important. What we can quickly derive is what's important, right? Okay, everybody understands about vector norms now? And vector norms are pretty easy to deal with. Okay. What about matrix norms? Well, obviously they also have to be norms, so they have to satisfy the same conditions of the norm, right? So you have, what is it? Positive definiteness, homogeneity, and triangle inequality. But now what we have is we have a function that goes from all of the n by n matrices to a real number. Okay? And for that you have to satisfy the same conditions, and since I have notes, let me just pull up what those conditions are. Oh. I guess I forgot to define matrix norms. Oh well.
Is the second condition same for the matrix norms, or should it be alpha to the n?
No, it's actually alpha. We'll see that it's alpha times this matrix norm. Okay. So let's just start with some examples. One example is known as the Frobenius norm. And it is defined as the sum over I, the sum over j of the absolute values of the entries. Square. Square root of that. Right? How can we think of that? Well, we've got a matrix. We've got columns for the matrix. Take all of those columns and stack them on top of each other. Think of that as a vector. Take its 2 norm. Yes?
Even darker marker.
Oh, yeah.
So light.
Sorry. That probably just makes it worse, right? Anyway, you get the idea. Yes?
It's quite different on the.
It's quite different.
Yeah, it says P root of.
Oh, that's just because I copy and pasted wrong. So thank you for catching that. I'll fix it before I put the notes up. I can't reach or I'll have to go and erase it. All right. I did that once in a presentation at Intel. I went and wrote on the screen. Not very clever. They still give me money on occasion. I don't understand. Oh, maybe it's that group that no longer gives me money. All right. You get the idea, right? And you can imagine that if you look at it this way, it shouldn't be too hard to show that it's positive definite. That it's satisfies the homogeneity condition and that you can establish the triangle equality, right? So we'll leave that as an exercise. Now, you may ask, now, obviously we could have taken rows and stacked them on top of each other. And then another interesting observation is, look, when you store matrices in a computer memory, you have to store them somehow in a linear memory, and therefore you go and you take these and stack them on top of each other anyway. That's called column major order storage. So these kinds of ideas are out there and not that hard to imagine. One thing you may ask yourself is, well, why didn't we just call that the matrix 2 norm? Okay, and that's because we have other ways of defining the matrix 2 norm that are much more intuitive, well, that are much more useful because they relate nicely to the vector 2. It is, of course, the case if matrix A has one column making it a vector, then the Frobenius norm becomes the vector 2 norm. So that's kind of nice. Obviously, we can similarly define matrix norms that simply use, for example, the vector 1 norm or the vector infinity norm, where you take the columns of the matrix and you stack them on top of each other. And for some reason, people don't tend to do that, so that mustn't be all that useful either. So what are the useful ways of defining matrix norms? The Frobenius norm actually is useful, both theoretically and practically, but we'll get to that later. Let's erase. Well, we want to keep this. Let's talk about how the induced matrix norms work. In the notes, I do this in more generality than I'm going to do in class, because in class I'm going to focus on the ones that we actually are going to run into and that are useful. Okay? So let's start with the vector 2 norm, and let's think about how we can define a matrix 2 norm. And for this, we have to think about what it is that a matrix does. Okay. Now, notice that if you have a vector x and you look at A times x, then if you multiply x by some scalar and multiply it by a, the alpha just comes out. And the point there is that it suffices to look at how a matrix acts on all of the vectors on the unit circle, because if you know how those are changed by the matrix, then any vector that's just a multiple of the vector on the unit circle, you can figure out how that is transformed as well. So the action of a matrix is really defined by how it acts on the vectors on what's known as the unit ball. In this case, the unit ball being measured by the 2 norm, the vector 2 norm. Okay. And what happens is that A takes the unit ball. Of course, in higher dimensions, this is a little bit harder to picture. But it takes that unit ball and it kind of makes it into an ellipse. Okay? And for these norms, the size of the matrix, the norm of the matrix, is defined by how it takes a vector of length 1 and stretches it into a new vector, and the size of the matrix is then defined by the maximum that this vector can get stretched by the matrix. Okay? So how could we define that? Well, there are actually 2 ways of defining that. And that is either as the 2 norm is defined as, of the matrix A, as the maximum over all vectors of length 1 of the length of the result vector. That's one way of defining it. A second way of defining it is to say that it's the maximum over all vectors that are not the 0 vector, because obviously asking how the 0 vector is stretched is meaningless. It doesn't get stretched. of the ratio, because that just defines it for all vectors. This here defines it using only the unit circle. You with me? Now, if there are really picky mathematicians in the audience, you should notice that we say, well, we don't even know whether this maximum exists. After all, it could go to infinity, right? And particularly for this definition, that could happen. Now, these two, of course, are just equivalent because you can always look at this as the max over x not equal to 0 of a times x divided by the norm of x. And that's because of the vector 2 norm, you know, you can always take a scalar inside or outside in absolute value. And then you can just take this to be a new vector y and say, but we know that those vectors all have length 1, and therefore you get this right here. Okay, and that's how the two link. You sort of kind of with me? So strictly speaking, you should start by saying it's really the supremum, which means that it's a bound that you can get arbitrarily close to. But then those same picky mathematicians hopefully have taken enough mathematics to recognize that if you take the supremum over a closed compact set, then you actually will attain that supremum in the set, and therefore you can change it to the maximum. Okay, just a little technicality. But that requires you to have taken either real analysis or a course called advanced calculus, which is often the same course. And that's not a prerequisite for this course, and therefore, if that just went over your head, don't worry about it. All right? The important thing is to understand these kinds of norms define the size of A, which is the size of the linear operator, by how maximally the vector is stretched by the operator. Okay, that's really important to get. Okay, obviously you can define that kind of norm for any of the P norms. All right? So now we have a whole family of norms, and then the more general case with which I start recognizes that the norm you use on the vector that's input to A times x doesn't need to be the same norm as you use for the vector that comes out of A times x, and then you get an even richer set of possible matrix norms. Okay. All right. Now, all of this is written down in great detail as proofs. I think it would be useful to just prove that the matrix 2 norm is actually a norm, just to get some practice. Okay, what conditions have to hold? It has to be the case that if A is not the zero matrix, notice that the 0 here is the m by n matrix of zeros, then the 2 norm of A is greater than 0. Okay? And here we're going to get some practice with slicing and dicing. How do you do that? Let A be not the 0 matrix. Then you can write A as its columns. Right? That's the slicing and dicing that we talked about in the last lecture. Think of the matrix as columns. What do we know? Well, if matrix A is not the 0 matrix, we know that at least one of these columns is not the 0 vector. Right? A sub j is not the 0 vector. Okay, so we pick J to be the index of the column that has a non-zero in it. There could be many such columns. We'll pick one. Now what do we know? We know that the norm of A is defined as the norm of A0, A1 through AN minus 1. That's not clear yet. Let's define it. It's equal to the max over all vectors of length 1 of A times X. It would be nice if we somehow picked an X that picks out the jth column of A. How do we pick a vector X that picks out the jth column of A? E sub j, right? The jth unit basis vector. So we know that this is equal to, no, we know that this is greater than if you pick a specific vector. So this is greater than or equal to A times E sub j. Am I missing something? Remember, this is the vector that is all zeros except the 1 in the jth position. Right? But we know that A times EJ picks out the jth column. That's actually how we define the matrix. And we said that is a non-zero vector, so this must be strictly greater than 0. You with me? Did I do it okay? Always speak up, because sometimes I make mistakes. And of course, I'm only doing that to test you, right? All right. Let's move on. The second thing we want is that if alpha is a complex number and A is a matrix, then we want it to be the case that alpha times A in 2 norm is equal to the absolute value of alpha times the 2 norm of A. Well, notice that the 2 norm of alpha times A is just equal to, we just go back to the definition. Well, there you know that you can bring this out because this is a vector 2 norm. And then you know you can bring that out here, and then you recognize that what's left is just the definition of the matrix 2 norm of A. All right? So that goes okay. I'm starting to go a little fast because we've got stuff to get through. And then finally, we have to prove the triangle inequality. So we need to prove that A plus B in 2 norm is bounded by A in 2 norm plus B in 2 norm. And again, every one of these proofs is the same. You start with the left-hand side. You write down what the definition is of this. Okay? Then we know that if you add 2 matrices and then multiply that by a vector, that's the same as multiplying them separately. So we get the max over all x equals 1 of ax plus bx. Okay? This here, we're taking the 2 norm of a vector because a times x and b times x are vectors. So we know that the 2 norm, vector 2 norm is a norm, and therefore the triangle inequality applies. So you get max of the 2 norm of x equals 1 of ax plus bx, except that's now an inequality, right? We've replaced this with something bigger. Now notice that here you're maximizing over x, and you really, it's the combination of the two that you're maximizing. Clearly that's less than or equal to maximizing the first term. And maximizing the second term separately. And adding the result. But this is just a definition of the matrix 2 norm of A, and this is just a definition of the matrix 2 norm of B. So matrix 2 norms satisfy the triangle. These are norms. This is good. And pretty much proving this for the matrix 1 norm or the matrix infinity norm is all the same. So we'll leave that as exercise. You guys know, right? Can't do everything for you. When you do these exercises, it's okay, as a matter of fact, it's encouraged to do it with other people, okay, as long as everybody learns. And it's okay to look at other material. But it helps, obviously, to try to do it on your own first. Any questions about this? This is pretty heavy-duty math, right? Not quite what you signed up for. Sorry. It's very mathematical. Clearly, I enjoy it. I love a good proof. Okay, so now what we have are, we have these norms that are associated with vectors. A very, very important property of these matrix norms is that they are what's known as submultiplicative. Okay, and what's that? Well, if in addition to the other conditions of a matrix norm, a matrix norm also has the property that A times B, and I'll illustrate this for the 2 norm, is less than or equal to the 2 norm of A times the 2 norm of B, then this is known as being submultiplicative. It's an additional thing. Now, it turns out that any matrix norm that is induced by a vector norm in this way, by looking at the maximal stretching, is submultiplicative. It turns out that the Frobenius norm is submultiplicative. But a whole bunch of other norms actually are not. So this is not something that every norm has. And how do we prove this for the matrix 2 norm? Well, we do it as always. We do A times B in 2 norm is, actually the way you do it is you start by showing that A times X in 2 norm is bounded by A times X. Okay. And how do you do that? We look at the 2 norm of A. It is defined as the maximum over all x not equal to 0. Ooh. I chose the other definition of the norm of A times x in 2 norm divided by x. Okay. Now we've got x's running around here, we've got x's running around there, so let's actually change this and let's call it y. We'll do a change of variable. But this is equal to ax in 2 norm over x for the x that maximizes. Now, do I care about that? No. What I care about is that this is greater than or equal to that for all x. Right? That's what I care about. And then all you need to do is bring this to the other side, and you get the result that you want. Okay, so this is true for a vector. And then if you look at the 2 norm of A times B, that's defined as the maximum over all x not equal to 0 of A times B times x over x, which is bounded by A in 2 norm times bx in 2 norm over x. Why is that? B times x is a vector, and therefore we can invoke this result right here. And then that is bounded by the 2 norm of A times the 2 norm of B times the 2 norm of x over x. Again, invoking that result, and then you cancel that against that, and you're done. I guess there's a little and you can cancel that because you chose your x to not be 0, right? And I think that I should have along the way carried through the max over x not equal to 0. But then once you get rid of the x, you get that that's just equal to the 2 norm of A times the 2 norm of B. All right? Now, you can pull this exact same trick for any matrix norm that is induced by a vector norm. Okay, so there's nothing specific about having chosen the 2 norm here. And I think I left doing this for the 1 norm and the infinity norm as an exercise, but you're going to find that that's pretty straightforward. Any questions about this? You know, in proving the triangle inequality, you needed the Cauchy-Schwarz inequality for the 2 norm, and that was kind of tricky. But every other proof, if you look at it, you know, all I do is I go back and I say, what is the definition of? And I start cranking through. The only tricky part is that sometimes it's more convenient to use this definition of the 2 norm or the vector-induced norm. Sometimes it's more convenient to use the other definition. And often as you're doing the proof, you kind of have to play around with it and go, oh, it seems to be easier if I just switch to the other equivalent definition of the. Okay. Unfortunately, we're out of time. So what I'm going to do is I'm going to start next lecture with how this all fits into our world. Okay. What was our world? Trying to figure out how to put bounds and how bad the solution can be relative to a perturbed right-hand side when solving. So go home and do some math. Oh, it's invigorating. Some people go and play basketball. You guys can show. You should go and do some proofs.